Okay, let's get started. Okay, so here we are on our last mountain of the course. I don't know if you remember this. This was our graphical syllabus back at the beginning, and we're going to be going over energy. So this is, I love this part because we've gone from the quantum realm, right, the particle in a box, all the way now to where we're going to be dealing with global use and consumption of energy. So like how much energy the whole globe uses. We've gone from the smallest energy units that we could think of, really, zeptomoles and zeptograms. I mean, like single particles almost, and zeptojoules. Now we're going to get up to exajoules, 10 to the 18 joules. So forget kilo, forget giga. We're doing giga times giga, so a billion. And it's just mind-boggling, the scale of the numbers. And so this is always an exciting part of the course, I think. It is for me. So let's jump over to our notes. Now we're going to start with all of the combustion sources of energy that power our daily lives. So let's just make sure everything is squared away. Looks like it. And so we're going to be talking in this section about all the sources of energy that we use, the sinks, where the energy goes, and the conversions. Is it not? It was. I remember seeing it earlier.
As soon as you switch tabs.
Really? Is that what did it? Okay. Why would that matter? All right, let's try to just pull the plug and push it back in, see what happens.
Isn't that great in 2022?
Yeah, I know. Pull the plug and stick it back in, see what happens. Yeah. The computers do make you insane. They say the definition of insanity is doing the same thing, but expecting different results. But computers force you to do that. They really do. I mean, you try it, it doesn't work. You try it again, and it works. What is it with USB drives? You put it in, doesn't fit. You turn it over, it doesn't fit. Then you put it in, it fits. Always three. No, that's the way it is. It's so stupid. Yeah, but anyway, that's the way it goes. And so based on that first law of thermodynamics, energy can't be created or destroyed. And we'll find when we get to the nuclear part, not today, but next lecture, that it's really energy or mass energy. Mass and energy are interchangeable. It can be converted one to another. And so mass does appear to disappear and appear, okay? But it's because it's being converted into energy. In fact, when they were discovering the nuclear processes, they called it mass defect, and we'll get into that. Like there was missing mass in the products, and they're like, what happened here? And that's where that equation E equals mc squared came from. So energy can't be created or destroyed, so the total energy of the universe, as far as we can tell, is constant. And it's just shifting from usable energy to unusable energy. So that's being driven by entropy. So you could think of another definition of entropy as sort of the unusable energy. So energy's gone through a process and now it's being lost to random motion. It's gone through systematic motion, and we've tried to get as much work out of that as possible. That's where efficiency comes in. And in converting that useful energy into unuseful energy, or energy that's difficult to capture, we've used entropy to drive these things forward. And so this whole part of the course is in how we're converting useful energy into less useful or non-useful energy. We're losing it in terms of gases, which expand randomly in all directions, or in radiative heat, really low frequency infrared and radio wave heat that's lost to space. There's no way to capture that energy back. And so we're constantly radiating this energy out to space. And if we capture some of that energy by our atmosphere, in terms of water and CO2, that's what keeps us warm at night. And so we'll talk about the greenhouse effect and how we don't freeze when the sun goes down. Okay, so this is a chart that I pulled from Stanley Manahan's book, Environmental Chemistry. When I was at West Texas A&M for 4 years, right after graduate school, this was one of my courses that I had to teach. So it was fantastic. I learned a lot. It taught me that water is not H2O. Water has all kinds of critters in it and, and mud and stuff like that. So environmental chemists, the water is not H2O. Water is all like natural waters and so on. So I learned a lot in that course. This is one of my favorite things that I learned was all of the different conversion efficiencies. So we can walk around this chart. What we're dealing with most of the time is fossil fuels, this chemical fuel, but it could be also renewables. It could be wood and peat bogs and so on. But we'll take that chemical fuel and we'll mix it with oxygen in the atmosphere and create a fire and capture that thermal energy. So we can convert that chemical fuel into thermal energy. And these would be the efficiencies that we could use. The most efficient way that we've developed is just making steam with that. And so once we get water up to its boiling point, 88 joules out of 100 will go into the steam. So we'll be generating very efficient conversion of that chemical energy into hot steam. But sometimes we want to move things. And so mechanical energy, we can spin a turbine. So we can take that steam and push it through blades and use some of that heat of the steam to spin those blades, and then we have mechanical energy. If we want electricity, then we can run that through an electrical generator and take, again, 100 joules of spinning motion can create 98 joules of electricity. So that's very efficient. But all three of these, if we want to have, say, a coal-fired power plant, if we have 100 joules of coal, of energy in coal, then we multiply that by that thermal efficiency, then it's 0.88. And then the turbine is where we really take the hit, 0.46. And then the electrical generator is pretty good, 0.98. These efficiencies are multiplicative. So what's our overall efficiency? So could somebody punch that in?
39.6.
39.6. 39%. So we're taking 100 joules of coal or natural gas or whatever, and we're only getting 39 joules of electricity out of it. And that's the best. Yeah. So this is our friend, right? I mean, this is our enemy right here. If you wanted to pass Elon Musk in terms of your amount of money that you've made in your lifetime, figure out a way to get past that 0.46. That's killing us. So anyway, y'all, I have no idea how to do that, or I'd be doing it. So you guys go out and fix that problem, make a better way to get through thermal to mechanical, or go straight from thermal to electrical. Just forget the mechanical and go through thermocouples. Well, that hurts right there, right now. You could fix that 7. If you could get that 7 up to 48%, you'd pass the whole steam loop, the whole or maybe even go straight from chemical fuel to electrical fuel cells, 40%. That's pretty close to the 39. So this is a great chart looking at all the different ways we convert energy. Well, we have solar cells too. Well, they're at 15%. If we get those past 39%, then we can go straight from sunlight to electrical and skip the whole fossil fuel, thermal, mechanical turbine thing. So all of these different routes, this is what I mean by energy conversions. This is a fantastic roadmap of how we get our energy and where the joules are stored and how we can convert from one to another. So get your imagination going. Here's the U.S. energy flow in 2002. And you might say, well, that's a little bit old, but I looked at this. It hasn't really changed because we're dealing with such large numbers that they don't change very much. And so I looked at, I found on the Energy Information Administration website, the EIA.gov down here, they track energy use in the United States and all these different sectors. And you can look at the total numbers, and they bounce around, just a few percent, maybe 5 or 6% year to year. There was a dip, of course, during COVID and so on, but we're back up. So, yeah, so I always check these numbers. I've got all of these numbers in this particular PowerPoint presentation. And so I haven't gone through and changed them all because every year I check and say, yeah, they still apply. So don't look at the 2002 and say, oh, well, that's, that doesn't apply anymore. It still does. So they've gone from exajoules to quadrillion BTUs for some reason. Why they went backwards, I don't know. But a quadrillion BTU is a 10 to the 15th British thermal units. So that's what this BTU is. I don't know if you knew that. British thermal unit. But it's essentially an exajoule. So 1.055 exajoules is a quadrillion BTUs. And our net primary use is around 100 to 115 exajoules per year. So that's huge. Now we'll look at what an exa is in a second, but let's look at these efficiencies. I like this chart because it has all of these different sources of energy. So let's look at the electrical power grid for a second. So we have 23 exajoules of coal. 21% of those are going into our electrical power grid. Natural gas, about 20.6 exajoules. 6 of those are going into the electrical generation. A biomass, 0.04 exajoules. Hydrothermal, 2.7, and nuclear, 8.6. And then electrical imports, like if you live in a border town with some other country, you might import some electricity from that other country. And so that's 0.08. So our electrical power sector brings in 40.3 exajoules. So that's what our consumption is in terms of our power grid, 40 exajoules. How much electricity do we actually sell? So that we have a track on that too. It's like of the companies that sell electricity, they add up all the exajoules that they sold, it's 12.5. So this is the joules of electricity sold. This is the joules of electricity bought. And our efficiency is 0.31. So we said the maximum would be about 0.39. So we're in the ballpark, and we're above 30, but still, where's that extra going? It's just lost. It's load leveling problems. You know, you've got the power going really strong because it's a hot day and a cold front comes through and everybody turns off their AC, and the electrical grid has to, switch over, and they lose some electricity and some power generation. Anytime there's a sharp change, you lose some efficiency. Yes?
Do you think that is actually going to change drastically with the push to EVs because they're going to be such a drastically larger drain on the grid?
Yeah, I don't think we actually have the grid infrastructure to handle.
I've heard that we don't.
Yeah, that our neighborhoods, that our houses are made like 100 amp boxes, and if everybody ran 100 amps into their home, our little substations wouldn't be able to handle the drain. So, yeah, there's going to have to be a lot of changes that go into, equipping us for electrical vehicles. Yeah. In terms of transportation down here, now this one I'm kind of confused on because I don't know how they measure this number. Right? Because I start my car, turn on the engine, I drive to work, turn it off, and how do they know how many joules it took to get me from A to B, and how many joules are wasted at the stop sign or at the red light, and so on. So I don't exactly know how they get this number. I guess I could pull that report and read the fine print. So I haven't done that. But anyway, they calculate the transportation as 20% efficient. Okay. So that, again, I don't know how that number is calculated, but it's definitely less than the electrical. And we saw that mechanical to electrical, so this would be the electric motor going from electrical to mechanical. So that would be the electric motor spinning your wheels, turning your wheels, pushing your car. So, it's got a wide range of efficiencies. Again, I don't exactly know when it would be 60 and when it would be 90. But the gasoline engine, about 25% efficient, and the diesel engine, 35% efficient, going from chemical to mechanical. So there you're skipping this thermal loop, you're skipping the steam turbine, but still piston engines we saw from the Carnot cycle, it's really hard to get those to be more than 35% efficient. Okay, so this is, again, Carnot cycle type efficiencies here in these piston engines. But they're going straight to mechanical, and that's what we want. So that's our vehicles right there, using chemical liquid fuel and turning it into mechanical energy. So we know that these are probably topped out at 25 or 35% efficient, but you throw in traffic and red lights, and you're going to come in at less than that, so 20%. So I know this isn't above 25 or 30, but it's, where they got the 20, I don't know. But it's not like we're going to go up. If we're burning fossil fuels to make our electricity, we're topped out at 31%. we're comparing this 20% in transportation to 31% in terms of our electrical grid. So yeah, if you narrow your efficiencies down, then you're kind of getting a false picture. And that's one of the goals of this particular set of discussions in this lecture, is to say we really should broaden our view. Instead of saying that this electric water heater is 98% efficient because it takes in 100 joules of electricity and generates 98 joules of hot water, okay, puts 98 joules into that water, that's really not an accurate picture, right? Because where do we get the electricity? So to me, an electric water heater is an incredible waste. Why? Well, because if I go back here, I can take that same natural gas and create hot water at 88% efficient, and it goes straight into the hot water, okay? If I want to use an electric hot water heater, I've got to go through 39% efficiency in generating electricity, and then go, let's see, so I generate electricity, and then I go back to heat through this hot water heater. So I've burnt natural gas, I've spun a turbine, I've spun an electric generator, and now I'm heating water with my hot water heater, and the Home Depot is telling me it's 99% efficient. I'm sorry, it's not. It's 39% efficient at best. So we need to think about what our resources are. We burn natural gas to make the electricity, which is the best at this point, like top of the line way to make electricity. And then we're heating water with it when we could have just burnt natural gas to make water. And we would have saved an enormous number of joules and resources. So if you want to heat something up, burn something. And you double your efficiency, more than double it. Okay, so that's one of the things that just get broadening your view. Yeah, that electrical water heater is not lying to you. It, from electricity to thermal, is 98% efficient. But the broader view, if we want to take care of our resources, you want to heat something, burn something. And so then let's look at residential and commercial. So here, natural gas is coming in. So here we get an efficiency bump, because if we want to heat our hot water, if we want to dry our clothes, if we want to heat our house, we use a natural gas heating system. So if we're not using as much electricity for that, then we can bump that efficiency up. And here we have 15 over 20, so about 75% efficient for residential commercial, if we're using natural gas and those kinds of things for homes. Sometimes they use oil to heat homes, and so that's what this is, this 2.4 exajoules. That's the Northeast when they have oil delivery and you got a tank in your basement and an oil furnace. And then industrial, so they use a lot of their waste heat. So notice this lost energy is really low. So if you've got an industrial furnace that's doing your metal smelting or whatever it is that it's doing, and that waste heat, instead of throwing it straight out to the atmosphere, you run that through a heat exchanger, and that's how you heat your buildings. Okay, so then you're not paying to heat your buildings, you're paying for your industrial process and using waste heat to do things, and that's how they get up to 80% efficient. So we complain about large companies and corporations, but they actually do a great job at resource management, because that's their bottom line. The more they waste, that's like wasting money. Money's just going out, into the sky. And then transportation's a really tough one, because again, the Carnot cycle, piston engines are difficult. Electrical vehicles, again, if you take a broader view, we're going through a 39%, or in case 31% efficient electrical generation, and then pushing cars around. So there's no silver bullet really in these particular situations. So we just said energy can't be destroyed or created. So what does it mean by lost energy? Well, its usefulness is lost. Like in this building, our air-conditioned air goes out the hood and it's gone. It's in the atmosphere. How do we get it back? There's really no way to capture that. And so we call it lost. Most of the time it's in terms of steam or hot air, and then that's radiated to space. And then after we use the energy, it's also lost. And so, our vehicles, they have the tailpipe, and then that's lost. That hot air is lost. So overall efficiency of all of our processes in the United States is around 38%, mostly governed by the electrical efficiency. Okay. So, yes.
Are you going to be talking about in this section at some point, kind of the reluctance to use nuclear?
We'll get into that in the next several lectures. So we'll go into nuclear and in detail. Yes. Yeah. And so we have talked about nuclear, renewables, and fossil fuels. Okay. And so here, let's go over the metric prefixes again. So exajoule is way up here at the top. There may be higher ones, but this is the highest one that I use on a typical basis. 10 to the 18 joules. So look at all those zeros. Yeah, this is crazy. 10 to the 18 joules. That's a lot of joules that we use. We use 100 of those in the whole United States. Yeah. Worldwide, we use 475. Yeah. Yeah. And then we did small numbers, right? Picoseconds, femtoseconds, anyway, so you've seen this. And so then let's talk about the energy content in natural gas. So the economy runs on billion cubic meters, not grams of a substance. All right. So in chemistry, we're always talking about grams and maybe kilograms. Oh my gosh, or a kilojoule. Oof. And we're talking about exajoules, like puny little kilojoules right here, So it's just silly. Okay, so what on earth is a billion cubic meters? Okay, so we buy that. If you see natural gas reserves listed, they're listed in terms of billion cubic meters. And so how many moles is that? So we've got, 10 to the 9 cubic meters that convert it to liters. Ideal gas law, so that's how many moles at standard ambient temperature and pressure. So that would be 298 and 1 bar. Okay, so how much energy is in a billion cubic meters of natural gas? So natural gas is methane. We know that reaction. Just react it with CO2, with oxygen and make CO2 and water. And so we could go through our delta H of reaction, look those up, those enthalpy of formations, the products here. So we've got water and CO2. 2 waters, here's the enthalpy of water, here's the enthalpy of CO2. Subtract the enthalpy of the reactants. So here's methane, and then 0 for oxygen. I went ahead and wrote it out. So then we end up with 802 kilojoules. Okay, for just 1 mole. And so how many moles in a billion cubic meters? 10 to the 10th. And so we end up with 32.8 times 10 to the 15 joules per billion cubic meters. And so 10 to the 15th is, if we go back to our prefixes, that's peta. So that's a petajoule per billion cubic meter. Now that's just using our knowledge of chemistry, right? Methane as natural gas. Okay, it has a little bit of isobutane and a little bit of propane and so on in it. And so if you look at the World Energy Council, they sort of analyze the reserves globally, and they use energy content. So they do this conversion, and they estimate it should be about 36 petajoules per billion cubic meters of natural gas. And so we're just a hair low, but we're the same order of magnitude, just assuming that natural gas is methane. So that's pretty cool. Our freshman chemistry enthalpy calculation gives us this enormous conversion factor that's pretty much on target with what they use to estimate the energy content. Now theirs is a little higher because it has a bit of propane in it, a little bit of ethane, and other carbon, higher numbers of carbon atoms. So we did this with the QSR or QSPR lab. Remember that? We got this equation. This was for 900 compounds. And so carbon has got the biggest contribution to it. And so we get a lot of energy out of carbon. Here's the hydrogen content. And so those are the biggest 2. Notice the oxygen is negative. And so it's a really bad idea to blend in oxygen containing compounds into our gasoline, like putting ethanol in our gasoline. That's just a dumb idea. And we'll see in a second why that is. But here's, again, it's just a pretty good fit to all of these number and types of atoms that we have in our particular fuel. And so here's the specific heat, because we really don't really buy things based on moles. We buy pounds or we buy liquids in terms of their volume. But notice there's this trend here, this top numbers. These are the hydrocarbons. You say, well, you put nitro in there, it's like boosting car engines and so on by putting nitrous oxide and so on. Yeah, those actually don't give you more heat because of the nitro compounds. They're giving you more oxygen. So it's a way to put oxygen into the cylinder in like a liquid phase rather than a gas phase. So it's a way to stuff more oxygen in the cylinder. They're not actually giving you as much energy as the fuel is. Okay, but they're giving you more oxygen. So, but then the other oxygenates blended in, these are already reacted with the carbons. So like the alcohols and so on. So these will be alcohols and ketones. So OHs. So those oxygenated compounds, they have a smaller specific heat. They're not actually giving you more energy. And if you're paying for them and you're producing them, it's lowering the efficiency. Now, you might hear politicians talk about the hydrogen economy, because look at that number. It's ridiculous. So high, okay? But this is because this is by gram. And so this is the specific heat, kilojoules per gram. But we learned from our analysis of real gases that hydrogen is the least compressible gas. And so we don't buy gases in terms of their mass, we buy them in terms of their volume. And so it turns out that this is not a good solution for transportation because it's so hard to put a lot of hydrogen in a small space. It's the least compressible. And if you're going to attach it to a catalyst, then you're going to run into problems of putting it on the catalyst and taking it off, and then the weight of the catalyst isn't doing anything. So now you're pushing around for transportation the weight of the catalyst, and it's not helping you, except holding hydrogen. Yes.
I was just asked, is that why they're having such a hard time with like creating hydrogen fuel cells, like efficient hydrogen fuel cells for vehicles?
We'll see why. Like we saw that in the electrical chapter. There was it was rushed at the end of the slide. I showed a hydrogen fuel cell, and it was the proton transport membrane. So for high current electricity, we can move electrons at enormous currents, but we can't move protons that fast. And so the current limiting step in all of these fuel cells is how fast you can move the ions. You can move the electrons incredibly fast, but moving the ions is the thing that limits our power. So we can make hydrogen fuel cells for low current demand, but it's the high current stuff like transportation that really is a problem. So they want to try to combine it with supercapacitors that can hold an enormous amount of electrical charge. They can deliver the high current, high torque situation for accelerating. But then we charge them up with the fuel cell. Yeah. And so let's talk about the hydrogen economy. How many joules do we have in hydrogen? Well, we could just take the hydrogen molecule, the enthalpy of formation for that, and its enthalpy of combustion, and we end up with 9.3 petagrams per billion cubic meters of hydrogen. And so that's, we could compare that then to the volume of methane, which you can put in a given volume of methane so much more. You've got, twice the amount of hydrogen, and you've thrown a carbon in there. And so it's 36 petajoules per billion cubic meters of methane. So methane beats hydrogen bad. So methane's the way to go. So let's talk about oil. If I had to ask you, okay, chemist, what would you say oil is? It's a long chain hydrocarbon. How long the chain is, I don't know. So I just said 18. Okay, it could be 22. It's not going to matter that much. You noticed all those hydrocarbons was kind of straight across. So it's pretty flat in terms of you add more CH2s, you just get a longer chain, but in terms of per gram, you're going to get the same amount of energy out of it. So this is our 1 ton equivalent of oil. So a ton of oil equivalent is 1,000 kilograms or a million grams. We got the molar mass of C18H38. So this is how many moles of carbon we have. We take the combustion enthalpy of that particular substance, multiply it by this moles per ton of oil equivalent, and we get this many joules per ton of oil. So 10 to the ninth joules, so that would be a gigajoule. So 43 or 44 gigajoules per ton of oil. And then coal. Coal's easy, right? It's carbon. And so we could just take carbon solid, react with oxygen, and we end up with 33 gigajoules per ton of coal equivalent. And so the World Energy Council estimates oil to be around 42. So again, our initial guess was pretty close. Gave us 43 or 44. Oil's not pure. It's not pure C18. And so it's going to have a little bit of oxygen stuff in it, some sulfur maybe, and so on. It's going to lower that. So that we would expect the actual number to be a little bit low, but we got 90% of it. And the same thing for coal. This is for pure graphite carbon. The best coal ever, which you would never find. Okay, you're going to find coal has calcium oxide in it and all this other garbage. And so it drops quite a bit. It drops to 29 gigajoules per ton of coal equivalent. But anyway, those are the numbers that we use sort of at this World Energy Council to look at the energy content of the reserves around the world. So here's our summary slide and our World Energy Council numbers here. So if you're going to do a homework problem and it's asking you to convert this amount of reserves into how much exajoules you have or gigajoules, use these numbers. That way you're using the same numbers I used to make the answers, right? And so this would be the energy conversions. If you have 1 billion cubic meters of natural gas or some other gas, or natural gas, use 36 petajoules per billion cubic meter. If you have oil, use this one, 45 gigajoules per ton of oil, or this one is per ton of coal. So let's now take all of our reserves that we have worldwide and see how much energy we have in each of those. So here's our world combustible fuel reserves. And the world uses 425 billion gigajoules per year. So that's 425 exajoules per year of energy. And so how many tons of coal would deliver that amount? 14.5 billion tons of coal. That's the dirtiest fuel because it has all the extra elements in it, mercury, uranium, and everything in it. And so do we have enough to power our world? Yeah, we have 847 gigatons of coal. What about oil or natural gas? We have 209 billion cubic meters. Here's the gigatons of shale oil, 409, 223 gigatons of crude oil, 42 gigatons of bitumen and heavy oil. So of oil, we have 674 billion tons of oil total. And we use 15 a year, at least in coal. How much hydrogen do we have? Okay, 0. So hydrogen is really a storage medium. We don't get hydrogen out of the ground. We don't pull hydrogen out of the air. We have an oxidizing atmosphere. So the hydrogen economy is not realistic. I mean, we have to make energy and store it in hydrogen, and then we can use it. And so that's not going to be a perfectly efficient process. So I know it looks great. You have that energy per gram of hydrogen is like off the charts at 120, but it's not really realistic at this point. It may be a great storage medium. So let's look at these world energy consumption values. So this was in 2013, it was 6,000 exajoules in natural gas. I updated it when we started fracking for natural gas. We got it up to 9,000 exajoules in natural gas. Petroleum, 9,000. Shale oil, 17,000. Coal, 24,000. It updated in 2016 to 37,000. Nuclear, 9,000. And that's one pass nuclear. We'll talk about what that means. So that's how many exajoules, if we use the nuclear reserves we have now, run them through the power plant one time. In other words, we don't reprocess the fuel. Okay. So total non-renewable 65,000 exajoules. And remember, we use 425 a year as a globe. Okay. Renewables, hydroelectric 90, wind 630, biomass and wood 1300. So the World Energy Council, and looking at hydroelectric, they were saying there are certain regions where this makes sense. If we were to utilize all of them, we could get 90 exajoules a year out of it. Like, you're not going to get hydroelectric out of Texas, really. We don't have hot springs. We've got a Balmorhea, maybe a little hot spring, but it's not like up in Idaho where you have, you know, and near is it Yellowstone? What's the one with all of the, like, Old Faithful? Yeah. You know, we could get rid of our national park and run a power plant off of Old Faithful, you know, but I think it'd be a loss of, I mean, what's just more valuable, right? And then wind, there's only certain places and so on. If you utilized all of those windy areas, we could get 630 exajoules per year. But hey, that's more than our annual consumption globally. We have to transmit it some places. And then biomass and wood, 1300. So that would be growing our own fuel. So total renewables, hey, 2020. So we could cover our global consumption with renewables. We could do some sort of mix of these, whatever makes sense. So if you have let's put it in numbers. If you have a retirement account of $65,000 and your expenses are $425 a year, are you worried about supply? You got a few years, okay? You will eventually run out, but what we've noticed is, notice the green numbers, they've been updated, right? We find new reserves. And so it's not like this is all we've got for the rest of time, but still. We have 153 years of non-renewables. That's without technology improvements. So, but there's something not shown on here, okay? We have all of these. What's missing? What energy source was not shown?
Solar.
Yeah, exactly. So all nuclear and fossil fuels add up to 65,000, but the sun hits the earth with 5,500,000 exajoules per year. Wow. Now, I mean, it's the whole planet, right? We got a pretty big planet. So if you add up how much the sun is hitting the planet, that's how much energy we're getting hit with every year. Okay. But even if we convert it, like 1.1% would yield 825 exajoules per year. Like, you could cover Louisiana with solar cells and get 425 exajoules per year. And some people are like, let's go. If you're from Louisiana, maybe not. You'll be like, hey, what's the deal? You know. But yeah, if we could harvest 15% of that energy, you know, with current technology, so there's room for improvement. We could get, you know, 825,000. What are solar panels? So current technology, 15%. If we could get 15% of that energy, that's 15% of the whole globe, which we're not going to do. Yeah, you know, but you know, yeah. So it's pretty interesting. So conclusion: there is no energy supply problem. There's just not. Okay. And that's also with nuclear. We haven't talked about reprocessing fuel. Okay, so I'm gonna run through these quickly because we're running out of time. But I do want to just talk about the issue is not supply. So when people talk about we're at a tipping point, we're running out of energy, they're just uninformed. We're not running out of energy, but we may need to think about pollution. So this is the best definition of pollution I've ever come across. Loss of control of a concentrated substance that causes harm. So there's 3 components to it. Okay, so harm is subjective, right? Is it toxic, acutely toxic, or chronically toxic, right? Concentration is subjective. Okay, so again, is CO2 in the atmosphere at 500 parts per million toxic? Is 600, 700, or is that, you know, such a good thing for plants? Again, you're going to have different opinions on that, but control is not subjective. You either have control of it or not. And so that's what we focus on. We focus on, do you have control of your output? And so solids are easy to control. And liquids are prone to leak. If you have tanks with liquid waste, you've got to make sure that you monitor that. And gases are difficult to control. And so we try to scrub our gases, to scrub all of the harmful components out of those gases to turn them into a liquid aqueous form. And then we'll boil off the water and trap those gases in a solid. And so now we have solid waste from our coal-fired power plants. And then where do we store that? Well, it's mostly calcium oxides and then trace elements, and we blend it into concrete. And so our fly ash is blended and ground into concrete resource material, and then they make concrete. So that's what we've done with our waste. And it's a solid, it's not loose, we have control of it. So that's pretty cool. And then for nuclear waste, we take it, we mix it in with sand, essentially, melt it, and make a glass out of it. And so all of those radionuclides they make radioactive glass with it, and then you store that. And so that's, again, a solid is easy to control. And if it's controlled, it's not pollution. It may be waste, but it's not pollution. Okay. And so the idea is avoid gaseous pollutants. So if you have a way to avoid those things, then you can keep control of your waste. And this is just a quick slide. We'll finish with this one. Notice the gross domestic product has increased 126% since 1980. Vehicle miles traveled, 91% increase. Population has grown 34%. And energy consumption really tracks with population growth. Okay. And CO2 emissions has tracked with population growth. But aggregate emissions like sulfur oxides, nitrogen oxides, and other kinds of things during this time has dropped because of stack scrubbing and so on. So we've really done a great job of controlling pollution in this particular case. And this is from that right-wing site, the EPA. That's a joke. So this isn't something from, pick your whatever. So low sulfur diesel and catalytic converters and stack scrubbing has really done a great job. So, okay, well, unfortunately, we're out of time. Look through the rest of those notes. You'll see some interesting stuff.